Good morning, everyone. I'm Henrik. I'm probably like everyone else trying to figure out this new platform. So my challenge here is to disable a lot of notification that pops up on my screen. So bear with me. But it's exciting to see everyone joining here. I will see if I have the permission to mute. Maybe someone else did it for me. Thank you for that. No, I do not have permission to mute everyone. So. Oh, I do, actually. Okay, that's good to know. We have 28 counting here, and more people are joining. And I still haven't figured out how to mute my notifications that pop up on the screen, so we might see those during the talk or presentation and the tutorial today. But hi, everyone. We have 46 registered, 32 are now online, so let's wait a little bit longer, especially since this is the first time for everyone here. Okay, It's 7:05. We have 37 people joining. And let's get started here. Sharing screens. And I am going to share my whole screen here, because we're going to need that throughout the talk and presentation. So, can everyone see my tutorial overview page now? Yes, thank you. Because I can't see you now, and I only see my own screen here. And I have a chat on the side here too. Thank you. So today's tutorial is an introduction to Futureverse for parallel processing in R. And practicalities. When you registered online, it said 2.5 hours, and but we actually have 3.5 hours slot. So I tried to adjust it so it's 2.5 hours for the main materials, and we have another hour optional if you want to stay on longer. This is the first time I'm giving a tutorial on Futureverse, so I wasn't clear how I should do this, but my disclaimer was I decided to go with the book down tutorial and scroll through this. So I'm not going to use slides here. I'm going to use some interactive coding while doing this. So I'm going to go between RStudio, the R terminal, to demonstrate a few things here. The objectives today is that if you don't know about parallelization but want to learn about it, the goal is that you will find it less magic at the end. There's nothing magic about it. It's also, I'm hoping it to be less intimidating if you feel it's like overwhelming right now. Ideally, I like you to feel comfortable to start parallelizing your own code at the end of this. And also, there will be some take-home message specific to the future framework and the Futureverse. And that will be that you understand that it's significantly lower the bar to get started with parallelization compared to other frameworks. It will help you and guide you to avoid common mistakes and issues that you otherwise experience. And it will take care of as many things as possible that you otherwise have to worry about. And that if you use it, it's future-proof, pun intended, but it will be able to scale when there are new parallel backends, for instance, coming. And it keeps getting improved all the time. Okay, so I saw a notification. Someone thought it was a very small font. Good point. I'm going to increase this and hopefully. So I'm presenting on a 15-inch laptop. So, but okay, great. Someone said, they asked, can I go full screen? I don't know. Can you do that? Or are you seeing my presentation in a small window? Okay, thank you very much. So I will try to maximize the font size here. Okay, let's see how this works. Okay, so since this is online and not in classroom, it's going to be very hard to do the classical tutorial workshop where people are working on things and trying things out and raising hands. And so I'm going to do a walkthrough instead, but feel free to try the different examples as I do them or later. Most important thing, feel free to interrupt for questions at any time, especially clarification questions. So think about it. Think of it as classroom tutorial. There you're like, I want to know things. I don't understand things, so just ask along. And as you know, there is a Q&A thing. So we have the chat, which most people discovered. And there is a Q&A tab that you should see too, where you can ask questions. I never used that, but as far as I understand, I can choose to answer the question here live or through the chat. And I think other people can also help answer or comment on them, but I'm not 100% sure about that. And rule number 1, there are no stupid questions, period, true, whatsoever. We're all here to learn things. So if you're sitting on a question and feel intimidated asking it, please don't feel like that. So just ask it. And of course, you can always reach out to me afterwards too, in private or on the GitHub issue trackers. The tutorial should now be available here. To be, let's see if I can open this. It is on this address that you, as far as I understand, you got an email to the Futureverse page that links to this. It's correct. Otherwise, oops, sorry. Did you all get this email to reach this page, or did anyone get this email? Yes, we did. Beautiful. Thank you. So at the bottom there's the link to this. It's a link to the discussion page. Don't use that now, but there is also, if you click here, you can find this tutorial. So this is the material I'm walking through right now. Okay. So there you can cut and paste if you want to, or scroll back if I move too fast. And after the session, you can ask questions here on the discussion forum. That's a good place to ask questions. Okay, so the agenda for today. This is a very rough agenda, but I'm going to give an overview of what the Futureverse is. Then we're going to move into the core of the Futureverse, which is a package called Future that provides a few basic functions. I'm going to see if we put in some breaks now and then, so we can stand up and stretch. And I'm going to need a break too. Part 3 will be relieving the core framework and using something we call MapReduce APIs, which is what most people use. It's like Future Apply, For, and For Each, if you heard of those. And we're going to get into some details, but I think they are very useful to understand. And that's what makes Future so easy to use. I titled this one. Because it comes with some benefits that you won't have in other parallel frameworks in R. And also, beautiful things. We're going to have, I'm going to show you how you can report on progress updates, for instance, progress bars in parallel processing, because that's a very frequently requested feature. And so about this time, we should reach 2.5 hours, I think. And then I'm going to do a quick summary and comparison to other parallel frameworks. It won't take much long here since we know most of it's been already covered. There is a topic that is very important, especially if you're into science or statistics. It's about random numbers and reproducibility, which is sometimes a problem when you do parallelization. And then I'd like to have an open discussion. And of course, we're going to have, there's room for questions and answers throughout the whole tutorial, so not just at the end. So I've created a few polls here to understand who's who. The one I actually forgot now, I should ask from the beginning. I posted it now. Do you see that? It's saying radio check. How's my sound? So please fill that out. So I want to make sure I'm loud and clear to everyone here. And then I'm going to, after that, I'm going to launch another one, which is asking you how much you know about parallelization right now. And okay, let me launch all of them. Third one is what's your main operating system? I hope they come in the way I'm submitting them here. And I also asking you how you normally run R, like Terminal, RStudio, VS Code, etc. Now, I'm very curious if I can see the answers. Okay, I'm launching the last one. I can't see any answers yet. Do you have access to a cluster? I'm going to throw that. So there are 5 of them. So I don't see any results. I just see them being submitted. Might be able to see them when I end them. So let's keep them open for a while, and I keep talking. Okay. Okay, so I'm going to check in on the polls in a few minutes here. So why do we parallelize? There are different reasons why we do this. The most common one is we want to speed up processing. And what that means is we want to speed up the processing so things finish sooner in terms of wall time. So instead of you having to wait 20 minutes, you might only have to wait 2 minutes for your results to show up. So that's what we mean by speed up, the waiting time. Sometimes we can also use it to lower the memory footprint. And that's more distributed processing. And that's because if you have a big calculation, you can actually split that up and send it out to multiple machines. And that's, so you can, if you can't fit it in memory on one machine, you can split it up on 10 machines, and each machine only needs 1/10 of the memory. That's the ideal case. Sometimes we also want to do avoiding data transfers, and that's, we're not addressing that really here, but you can imagine like the field of astronomy, where they have the big telescopes. Their raw data is so big, so they can't transfer the data from the telescopes to some central place. So they have to do pre-processing out remotely and then bring in summarized data back centrally. So you can imagine that model too. And you see that in things like Spark in various distributed databases. And then there are other reasons too why we parallelize. And then one is asynchronous user interfaces, and we have that in Shiny. So when you click on a button to do something, to run something, and that thing takes more than 5 seconds, you don't want an interface to freeze up. So you want to process that in the background, and that's one type of parallelization. I'm not going to talk about Shiny in this tutorial, but it turns out that futures are widely used for Shiny. Let's see, there was one question here. Does using a multi-core processor provide the same parallelization advantages as a cluster computer, though on a smaller scale? We can get into those details later, but parallelizing locally on the local machine is often faster than distributing it across multiple machines. But of course, if you have multiple machines, you can do more things. So you might increase your latency for each task, but your throughput will increase. Okay, let me close the polls here and see. Okay, radio check. I don't know if you can see the polls results now. Can you do that? Anyway, there's one person has quite poor quality. Okay, so you cannot see them, so it's only me. So one reported 2 on the radio quality. 3 people said okay. 4 people said great. No, 17 people said great, and 17 people said perfect. So I will assume it works. See if I can close it to my microphone. Okay, let's see for the other one. How much do you know about parallelization? So 30% of you, 12 people said, I'm new to parallelization in R. That's great feedback. So I will try to be very careful and slow here to explain things, and please ask questions. 46%, 18 people said, I tried the basic, for instance, parallel package and for each, but that's it. 6 of you, 15%, have already used the Future framework and want to learn more. And there are 3 people here that say they have a good understanding of the different parallelization solutions in R. Okay, that's very useful feedback from here. So I will as the title said, this is an introduction to the Futureverse. So that's where we keep the focus here. But there will be room for asking technical questions too, especially at the end. Okay, operating systems. We have 30% on Linux, 30% on Mac OS, and 40% on Windows. And 1 person using the web-based RStudio Cloud, which is basically a Linux environment. So that's what's interesting. And then we have, how do you run R? So 20% of you run R typically in the terminal, command line, 70% use RStudio, and we have 2 people running in the R GUI on Windows, 1 person using VS Code, 1 person using Emacs, and there's another one which I'm now very curious about. So feel free to post what that is. Okay, and let's see. This is an interesting one. So do you have access to compute cluster? So 4 of you, 10%, don't even know what that means. We get to that slowly. 20% say you don't have access to that. And 12% of you say you have access to an ad hoc cluster of local machines. That's can typically be, there are like 3 different desktops running in the office, and you can log into them from each other. So those you can use for parallelization in R. Equally numbered, 12% have access to clusters in the cloud. So that could be like Amazon Cloud or Google Cloud. And a large number of you, 45%, 20 people, have access to a high-performance compute cluster with a job scheduler. Can only guess, but I assume that's very common in academia. So I think that's, I'll make an assumption that most of you are from there. Okay. By the way, another question. When I talk now, can you see more than my screen? Can you see me as well? Yes, okay, good. I wasn't sure if I was on video or you just saw my screen. Okay, exciting. So let's start with the future package. The future package, it grew out of real needs. Okay, so I see a comment that sometimes the video is on me and sometimes the screen share. So I don't know how that happens. But I hope you can see my slides, my screen most of the time. So it grew out of real needs, from scientific needs. I've been working in genomics, cancer research, bioinformatics, statistics for, 20 years now. It's designed to be a simple unifying solution for all parallel APIs in R. It's designed to be write once, run anywhere. It's 100% cross-platform, so if you write your code, it will work on Linux, Mac OS, and MS Windows. It's easy to install, very small footprint to install, and it's on CRAN, like everything else in this presentation. I would say it's very well tested. It got lots of CPU mileage, and it's used in production. And things should just work. That's, of course, that we all say that, but it's designed so you shouldn't add friction to your everyday work. It should just work. Of course, there are corner cases and things that you will run into, so you will notice it's there. And the design goal for the future package itself, the core, is to always keep it as minimal as possible. So bells and whistles and other things will be on other packages that builds on top of this. Okay, so what is it? It's I'm going to go through some code examples so we just make it less abstract, but I won't run them, I won't explain details, but at least you can see what they look like. So imagine this case. We have a variable x assigned 7, and we have a function that takes this x as input and returns the value into y. And this function is very slow. It's called slow, and it takes a minute to finish. Then we can have another function that takes half a minute and takes the same x input and assign it to z. So if we run this sequentially, of course, the first one takes 1 minute, the other one takes half a minute. So everything is done in 1.5 minutes. So we use the future framework. We load the package future. We use a command called plan multi-session. That means run in parallel on the local machine. And here is the syntax for the same thing. it's instead of just calling this, we now called the function within a future. And that's assigned to handle to the future. And that will take a minute, but it will run in the background. So immediately after this line is called, we get back to our prompt or whatever we have here. And we can call this another function. And we call it as before, we call that in the same R session that we are running. So that will take half a minute to run. And this one is still got another half a minute before it's finished. So when we ask for the value of this result, which we do with a function called value, this will now lock up for half a minute until we get the y. But all in all, this will now finish in 1 minute because this runs in the background and this run at the same time in the current session. So 1 minute. So that's the core framework. And what does it look like on things that we call MapReduce that we'll get to later? So this is where most people are using parallelization. So say we want to calculate this slow function now on a vector on 1 to 20. Since each call will take 1 minute, this is going to take 20 minutes to complete. With the future framework, there's a package called FutureApply, which mirrors all the base R apply functions, but can run things in parallel. And there is a setup where you say run everything in parallel on a local machine using 4 parallel workers. So what happens there, it will take this vector of 20 elements and chunk them up in 4 equal sizes, and each worker will process on a chunk which contains 5 elements. So, and since they are running in parallel, each worker will take 5 minutes to complete, and they will finish about the same time when we look at the the clock on the wall. So this is typically how you will use parallelization, most of you. And if you're using Tidyverse, we have per package, a very similar call there sequentially is to use the map function. It looks very similar to the lapply. And that will, of course, also take 20 minutes running sequentially. There is a per package that maps the per functions that we can use. And similar here is like a prefix future underscore map. That's, you only have to add that thing and you can run in parallel, and this will take 5 minutes. Then we have a famous package for each, which we can also use for sequential processing and parallel processing, and it's by far the most well-known. And one of the goals here in this talk is to clarify a few misunderstandings about this package to make your life easier. So it's a great package. So how we do that is sequentially, we load a package for each. We say for each element in X, we call it the C here, Z, call slow. And this is going to do that for 20 minutes too. And technical advanced people, we actually do want to put this one in a local environment, but I'll leave that for later. Same version, but in parallel. And here I'm showing how to run it with the future backend from the do future. There are other solutions like do parallel, do MC, do Redis, but I'm focusing on the future framework. So this is how you can run for each through the future framework. Load it, you set till for each I want to use this, and then you parallelize on 4 workers, and the code looks the same here. Okay, so you see there are different ways of doing the same thing here. Okay. So what is the future work? As I said, it's a unifying parallelization framework in R for everyone, from beginners to advanced people. And if you feel like you grow out of it, you can continue on with parallelization in C, C++, and things like multi-threading. So the Futureverse is parallelization using plain R code. There was a question advantage of the Futureverse compared to parallel. We will get to that much later. I don't want to get distracted here, but you will see this throughout the tutorial. What extra things you get with the Futureverse. And it's also, when you use the Futureverse, it requires only minimal changes to parallelize existing code. As the previous example showed, it's like there are a lot of one-to-one functions. You can just replace an lapply with a future underscore lapply, and so on. And again, repeating this, write once, parallelize everywhere. And it's the same code regardless of operating system. So you don't have to worry about that as a package developer. We will see that later. And also you don't have to worry about which parallel backend is used, because your code will look the same. It lowers the bar to get started, fewer decisions for you to make, especially up front, which sometimes is hard to get started. Should I use this parallelization method, or for each, for future apply, MCL apply, whatever? So you don't, this helps you making these decisions, because you have, it leaves the door open to do things later on. You can stay with your favorite coding style. That means you can use base lapply things, you can use per style, tidyverse style if you like that, or for each. The other things that we get to, it's, call it the worry-free. You don't have to worry about global variables. For those who have tried that, parallelization, you always have to tell the framework what should be exported. Things takes care of packages, loading of packages, output warnings, errors. It's just meant to work. There was another question here about MCL apply. We'll get to that too. Not requirement. Yeah, I will get to those things. You will see the benefits. You will see pros and cons with several methods here later on. So the Futureverse also takes care of to make sure things are statistically sound, random number generation. And remember this too, it's like, for me, developing this, correctness and reproducibility is the highest priority. Because if we start producing incorrect results, in the worst case, they're incorrect and you don't even notice them. Sometimes they're incorrect and give an error. But so that's priority number one. And you always have to think about those things when you do parallel processing. And it's future-proof also in the sense that there will be, and there are things coming in, new sorts of parallel backends. Things will make it easier to distribute in the cloud from your local machine, things like that. And as those are created either by me or other people in our community, they will just work in the future framework. So you can feel sure about that. Okay, so what is the Futureverse in terms of packages? So we mentioned the core future API. It's in the future package. And then we have MapReduce packages that apply something on an input many times. And there we have the future.apply package, the fur package, and the do future, which is an adapter to the for each, which means you can also use it for plier and biacy parallel. And then there are several parallel backends. We have the backends that comes built in with a parallel package, part of R, local parallelization, some MPI. You can do remote thing here. I put it in parentheses because it's actually quite tedious to do it remote with this package. There is the future.calr package, which allows you to do local parallelization on top of the calr package. And there is the future.batchtool package, which allow you to parallelize on HPC job schedulers, and there are more to come. And then there is a package called Progressor, which provides you with progress updates, and this also works in parallel. And I choose to say it's part of the Futureverse framework, although Progressor itself doesn't really know about futures. And futures basically don't know about Progressor. It's one thing it knows about it, but together they actually allow to report on progress in parallel. And exciting news, I actually noticed yesterday that it's 7 years ago that the future package was first released on CRAN. So it's a little bit of an anniversary today. But this work started, I would say, back in 2005 in different shapes and forms, because I worked, as I said, and I still do work in genomics and bioinformatics, and I've been collaborating with people on Linux, on Mac OS, on Windows, and with different skills and different versions of R and different sizes of computers. And when we've been developing things in, for instance, DNA copy number, we needed things to work for everyone, and we needed things to be able to scale up if people could scale it up. So slowly, things have been growing and taking different forms and trial and errors, and eventually that core future framework came out. And I should say that I reinvented the wheels because it's when you're happy with a solution and find out, oh, this seems like the way to do, like, then you have to go back and say, okay, someone else must have thought about this before. And sure enough, back in 1975, people came up with this idea, and they coined the term futures, and that's why I later found that paper, and that's how I named this package future. It was called async first, but so we're building on top of past research and past expertise. Okay, so who's it for? It's, again, I'm going to hammer this in. This is for everyone using R, so don't be afraid of using it. And if you run into issues, you can reach out on the future discussion forum on GitHub to ask questions. I would also say it's users with some experience in R, but you don't need to be an advanced R developer to do this. Anyone who wishes to run many slow, repetitive tasks, that's the Futureverse is a good go-to. Anyone who wants to support parallel processing without having to worry about details and later on having to maintain parallel code, because a very common thing is like you have sequential code and then you say, oh, I want to do parallel processing. And this is a very common design pattern. You have maybe an lapply in your function, in your package, and then you have a flag, an argument, when you call that functions of yours, saying parallel equal to true or false. If it's true, you have a if parallel equal to true, call for each, otherwise call lapply. And that means you now all of a sudden have two code bases you have to start maintain and make sure you test, etc. And the Futureverse allow you to just have one here. So in that sense, it's easier to maintain Futureverse code. And also, if you do asynchronous Shiny apps, it's ready to be used there. See if I can share this. I'm just trying to sell this for you to like get started if you ever worry. But usage, I looked at this last year. What's used out there. Of course, since it was COVID, there is a package epi now too on CRAN, which also have a nice web page that track current trends in COVID. And they use Futureverse to speed up their processing. Seurat is a large-scale single-cell genomics. It's very popular. They also use futures for parallelization. So if you run this yourself, you might have seen this, that you can parallelize locally or across many machines. And they also have web-based interfaces to this, which is Shiny-based, and they use futures to make that non-blocking. And as mentioned, Shiny has support for this for a combination of futures and a package called promises that allow you to do non-blocking interfaces. We have machine learning framework, the ML3, they do this, use futures to parallelize. Targets, formerly known as Drake, supports using futures. It also supports the cluster MQ for parallelization. But you can speed up targets by using futures. And I want to say something about quality and stability. It's been there now for 7 years. I'm trying to keep the API very, very stable and not breaking things. So if you decide to use this, hopefully your code will keep running 5 years from now too. 225 packages rely on CRAN, relies on this now. Uptick, it's here you can see on the non-log scale the release of futures, and now 225 on CRAN. This is the uptake on future apply, and FUR packages was released later. As a comparison, it's not a competition, but since everyone knows about for each, I have to put this in a log scale. So for each has a 850, I say 771 here. So about 800 packages depend on for each for their parallelization. When it comes to downloads, we can take the RStudio CRAN mirror and look at that. And if you compare, if you see how often one package is downloaded relative to everyone else, and if you average that over every 4 week, you can see that the growth of use of the future framework kicked in, and we are now about the top 0.9% most downloaded packages, which is about the same as for each. Okay. So if you use it, you're not alone. And every release is very well tested. I want to sell this point too. Trust here. Lots of continuous integration testing all the time. we use reverse dependency check from the RevDep package. So every time there's a new release, it makes sure we don't break any of the existing reverse dependency checks on CRAN and Bioconductor. And if we find something, I work with the package developers to adjust that before I make my releases. There is a future.test framework that asserts that parallel backends meets all the requirements. And then, since for each is so popular, and there are a lot of packages that depend on these, like the Caret package, GLMnet, NMF, Plier, TSP, etc. We actually inject futures into their test and example code and run that through the future package too. That makes sure everything keeps working if we change something. Okay. Hey, so if you want to need support in future, there's the web page, package help pages. They have all. Remember to increase the font, but they're all packaged down now, available online, so you can find vignettes and help pages online. There's a discussion forum on GitHub, so please use that if you have questions or general discussions or even feature requests. Should probably start out there. If you find bugs, you can use the issue tracker. And then if you wonder how to stay up to date, there are blogs posted on the Futureverse page, but they actually hosted on jotr.org. And I'm active on Twitter. Okay, so that was that to get started. Let's see. I want to go back to the agenda to see where we are. Okay, so we are at 7:52, and I want to start on this before we're having a break, and then we're going to have a break afterwards. Okay, so let's see if I'm trying to see the chat here. There's a question about are you being able to parallelize things with dplyr? I don't think there is any work done on that end. There was the what's it called, multiplier. So conceptually you could parallelize, but I don't think you can parallelize it from the outside. I think you have to parallelize from the inside. So someone has to write parallel versions of the dplyr functions. So I think that's the solution that we will have to wait for. But that's a good question. Okay. Let's see. 1 sec. Okay. So the core future API. This is the important things now. So now we're getting into the details and some real R here. So there are 3 atomic building blocks that we can use for parallelization. And they are called, there's a function called future. Let's see if I'm going to maximize this again. I'm worried that you can't see it if you're on small screens here. But, so there is the future function. It takes an R expression as input, and it returns a handle to so-called future objects. This function is non-blocking, and I say if possible. There are cases where it can block, but we will see that later. Most of the time considered as non-blocking. there's a function to query this future called resolved. So you can ask the future, are you done? Have you completed the evaluation of this expression? Okay, question about blocking. And I see I actually have a typo here. So this is not correct. This is a non-blocking function. So blocking is like when you call a function and it's either it has to wait for the results to come back and has to wait for a long time. So when we say we go to the first one, if we have an expression and we have a slow function here, we call its slow function and that takes 5 minutes to run. But when you type this into R, it will return to you immediately, but it will run this slow running function in the background. But for your end, it feels like, oh, it's finished immediately. If it would be blocking, in this case, we basically had to wait. We had to wait for it to complete, which had been 5 minutes. So in that sense, it's like it sends off this evaluation in the background and returns immediately to you. And it's true, someone comment here, I somehow swapped the text here. So this one is resolved. Let me actually fix this very quickly. No. Let me just do this very, very quickly. So. Okay, reload. Yeah, okay, here it's fixed. So, so when we send this expression off to be evaluated in the background through a future, we can then ask this object, the handle to this future, are you done or not? And that will return true if the future is resolved, otherwise it will return false. And this is non-blocking, so you don't get stuck, you don't get penalized for asking the question. And then there is the, please give me the value of the results. And this one, of course, if the results or the things are still running in the background, it has to wait. So this one will, if it's not already done, it will wait, and we're saying it will block until resolved, and then it will return. And if it's already ready, of course, it will be very quick to get the results back. So a future is basically, the concept of a future is something about, at some point in the future, we are interested in the result, but we don't really need it right now. But just like you tell the computer, at some point later, I will ask for the result of this. So please start working, and I will get back to you. And that's a little bit like how you can ask colleagues to do work, or someone else. It's like, yeah, can you please work on this? And then they will go back and work on it. And of course, you can keep calling them and nagging them, are you done, are you done, are you done? And you shouldn't do that too often, but if you do it occasionally and they say, no, I'm not done, then you wait maybe another hour and then you're done. And then you say, okay, now I need a value. I'm going to sit here and wait till you're done. And you get the results. So that's what you tell R to do with futures. Okay, so Here's a mental model. This is a little bit technical, but it might be something that clicks for some of you by seeing this, or it might click later. But if you look at a regular R expression, which we all are used to, so like you take an expression, and this is an abstract. The easiest expression is like 42. So assign 42 to the variable v. But another one could be one of these slow functions. So you say an expression is call a function and assign the results. So it looks like a single line operator for us, but what actually R does, it does this in 2 steps. It evaluates this expression on the right-hand side. That's step 1. And when it's done, it assigns it to the variable v. So you can think about the Future API as decoupling these 2 steps. Like this. You tell it through a future to go calculate what's on the right-hand side. And you say, give me a handle to this thing. And then later you can say, okay, now give me the value. And then you just use that regular to assign it. And this decoupling is key feature to all parallel processing. It's the #1 thing that allows you to parallelize. Okay, so let's see if we can actually do some demo here. Spin up our studio. Hope you all can see this now. Is that okay? Or should I go bigger? Let me go one more bigger. It will help someone watching this later to online. Okay, so now consider a very slow and kind of dumb function here, but for the sake of this tutorial, here is a way to calculate the sum of a vector x. You start out saying sum is 0, and then you iterate over all the elements sequenced along. The elements, we have 10 elements, is going to be 1 to 10 here. I use the KK index. And by the way, if anyone ever wonders why I put double KK or II or JJ, is simply because you can search and replace for it in the code much easier. So here is like, takes the first element, it adds it to the sum, and then just to emulate slowness, not only is this is a poor way of doing the summation, but then we're also adding a penalty of slowing down. So it takes time. So if we take this function, our studio here, now we have a slow sum. So if I do, you say every element takes 0.1 seconds. So if I do slow sum 1 to 10, it's going to take about a second here. 1 second. Okay. If we do a bigger one, okay, let's do this in the background here. That will take 10 seconds now to run. This is example of blocking. See, now the prompt is blocking me from doing other things. And now we're back. And of course, the sum 0 to 100 is 5050. Okay, so with the future framework, we can now do that in the background. So we're loading the future package and we tell it to run things in the background. That's this setting. And that slow sum x. So now look at this case of non-blocking, because we know slow sum takes 10 seconds to run here, but notice how it immediately returns. Oof, we're done here. We can do other things. Okay. Now, if we call this, probably went like 5 seconds now. Okay, we'll run 10 seconds, so we're done. But if we do this very quick now, starts 10 seconds, I ask for the value. Now it's going to block until that thing in the background is done. There we go. So when we call this, there are a lot of things happening. What the future framework actually does, it looks at this expression. It knows that, oh, I'm going to need a function called slow sum. I'm going to need a vector x, which we call global in this world. And then these components are all sent to the parallel worker, which then starts evaluating our expression. And as we're saying, the future function then immediately returns before the worker is done. So what happened when we call value here? So it will go and ask this future, are you done? And the future will actually ask the worker, are you done or not? And it uses internally using this function called resolved. If you look here, if I call resolved on this now, done. But if I start this and I call resolved, not done, not done, not done, not done, done. There we go. So, so that's how the value does that in the background and returns if it's okay. And as we saw in this example, if we call this returns immediately, so we can do other things. I calculated 1 plus 2 before, but here is like you can calculate the standard deviation. And this doesn't run in parallel because there's no future called in it. This runs in the regular thing. And we saw the resolve function. So that one is another important thing when it comes to parallel processing. It's not critical, but it's very useful because you can do other things. One thing is you can send a message, you can do other calculations, or you can actually also launch other futures. But let's see what this looks like. Cut and paste here too. We're starting this now. We prepare this. We're starting this future, and then returning back non-blocking is running in the background. And then I have a while loop that goes and check, are you done? As long as you're not done, print the message waiting, sleep a second, and so on. So now it waited 8 times, 7 times, but it took me 3 seconds to start it. So in total, the future was done after 10 seconds, and that's the value again. So here, function future, resolved, and value. They are the 3 atomic building blocks for doing any type of parallelization. And with those, you can build up much more powerful things. Hey, as I mentioned, we could, instead of just generating messages, we can do other things at the same time. So if you think about the summation, that's addition has this nice property. We can divide and conquer. We can take a vector of 100 elements and calculate the sum of the first 50 and the sum of the last 50 to get the sum of the parts, and then we can add them up. So you all know this in school, but if you have these 2 vectors, we can calculate the sum of those 2. And if we use this slow function, of course, it will take 5 seconds each. So there's no gain in doing this. Really, sequentially, we get the same result. However, when we do parallelization, we can now use futures. We can calculate the sum of these two halves in parallel at the same time. So I call it future 1 and future 2. And we can do other things here. And now we do this. We already done. Oops. Let me say just value f1 plus value f2. So just trust me here is like, since each of them takes 5 seconds and run in parallel, we can get the results after 5 seconds instead of 10 seconds. And if you have more parallel workers, you can split this up in smaller chunks and do things even faster. And the way to say how many workers you have is you say planned multi-session workers equal 8 if you have 8 CPU cores. If you don't do anything, if you just say planned multi-session, it will look at how many cores you have and use that as defaults. Let's see. I have some questions here. Okay, so I will go back 10 minutes here. So that was probably from the blocking thing. Yeah, sequential processing. Yeah, so let's explain that. Someone said if I use sequential processing. Oops. This will block. So if I do this now. This will now block until done because this runs on a single core in the current process. So that's one of the cases where it can block, which makes sense. It's I hope it makes sense. Another question, is it safe to use the package without explicitly calling future? Yes, you can do things like this. In this case, you have to do this. Otherwise, or this is the ideal thing. You don't have to do library, but you can actually do this too. And then this plan function is clever enough to look this up. So that works. Another, did you just have one parallel worker for that additional example? I don't know, I did not. Okay, and then there's a very important question saying, should you use cores -1 so you leave one open for other compute processes? This is a very well-known. Okay, I'm going to say this. This is the most common thing you see in this. Any code out there uses this. N-cores, parallel detect cores, a lot of examples, illustrations, stuff. It's you can do this, but I ask you not to use detect cores. I ask you to use this. Detect cores is too harsh, and we can discuss that later. You can do this, and actually, if you do this, you should want to do this omit equal to 1. And the reason for that is that this might actually return 1. If you do this, you end up with 0 cores. Omit equal to 1 will always make sure it returns 1. And there's a lot of code out there that use this or this. And if you run, for instance, if you have the free RStudio Cloud account, you only get one core to work with. And if you use a package that uses this or this internally, it's going to be an error. So I normally just use this, and I use all my cores, because there's always a little bit of overhead in the sense like waiting times, so it's safe. I don't stall my computers. Good. Another question is the number of cores relevant for a Windows machine? Yes. Linux, Mac OS, Windows, they all have cores. Most of our laptops have like 4 cores. Today, 8 cores. Some people have 16 cores. Bigger desktop machines have like 32 cores and 64 cores, but they have that. And yeah, so it's relevant for Windows machines. So the reason why I'm explicitly adding this just so people see, but most of the time I don't specify that. So let's look at this case. What happens with blocking? So here's another case. 2 workers now running in the background. So if I call these 3 functions, you will see that the last one actually block. And the reason is these 2 are keeping 2 of the workers busy, and not until one of those 2 are done, this one can start. So that's another way that things can block. So, which is good. So in this sense, you don't have to worry about, am I going to overuse all my workers? Okay. You can just create futures, and the future framework would just queue them up. If you run this very quickly, and when this starts, we know either of these 2 or both have started. So if you ask resolve done, yes, in this case, both were done. And this wasn't done, of course, until a little bit later. Okay. Choosing a parallel backend. That's done with the plan function. And this is actually something, if you write a package, you shouldn't use this. You should let the end user specify that. So we saw, I already mentioned, you can say plan sequential, and in that case, oops, should not have done that. There we go. We launch a future, it's going to run and block until it's done. So that's emulating regular evaluation in R. A multi-session is a parallel on your local computer. Happens under the hood, actually. So now we're getting into some details, but you might recognize it. It's actually setting it. So a question here, Heather, what happens if there is no plan? So sequential is the default. That's the design decision. Yep. Let's see. When you do multi-session workers equal to 2, under the hood is actually launching a cluster, so-called PSOC cluster, 2 workers. And then it's using something called cluster plan and use those 2 workers. That's kind of what happens under the hood. And this is very similar to if you would like set up a cluster using the parallel package with this function. So this is what I mean. There's nothing really magic happening. It's using the built-in thing. This is just like more convenient, less error prone and has more bells and whistles to do. So internally, when we run this, we're using the parallel package to parallelize. We can also run clusters in parallel across multiple machines. So this is how you would do it. So for this to work, if you can do SSH into a machine without entering a password, and there's R installed on that machine, this will work out of the box. And when the thing of SSH into a machine without a password sounds scary, but for you who don't know that, there is something called SSH key pairs, which is a very safe way to do this. So you generate private and public keys, and you hold on to your private key very carefully. And on the remote machine, you set up, you put your public key. The public key you don't have to worry about. You can spread that to the world if you want to, but and that means when you SSH into the machine, that your machine and the other machine will negotiate, and they will say, "Do you have SSH keys?" "Yes, I do." And then your machine sends an encrypted message to the other machine using your private key without revealing the key. And the other machine will then take the public key that you already gave it and say, decrypt your message, and then say, "Hey, it's you." So it's kind of you signing your login, and there's no one else who can fake your message. In order to send that secret message to log in, you need to have your private key. So if you can do SSH, and that's maybe we should show that. I do remote, let's see. Have a local Pi here. See, this logs into my Pi machine without entering passwords, and that's using this secret key exchange. So if you can do that, and you have R available on this machine, then you're good to go. You can specify the names of this machine. This is a Pi machine on the local network. This is a machine somewhere on the internet. And then there are ways to configure usernames and ports and things too. Yeah, someone emphasized it's very important to set up the public and private keys on servers. But if you do this, let me see if I can demo this here. Plan server. It took some time because it's starting and connecting to those machines. But if I now, let's see, if I use future apply package, I say, tell me about the R version, get R version. This is a good example. I'm creating two tasks, and since I have two machines, I'm hoping they end up on both, and I'm asking it to return the R version. You see, one machine is running 4.20, and another one is running 3.63. So that shows you how I'm actually connecting to two different machines here, which I find is pretty cool. It's and then we can use this to parallelize. So let's do that. Value F1. That's value F2. Boom. And so now remember, this machine can now be, I'm in California, this machine can be sitting somewhere in Sweden, and this one sits locally, and I actually asked that machine in Sweden to do this part of this calculation. And again, under the hood is the parallel package that does this. This is the workhorse for setting up parallel workers, and takes care of a lot of things, reverse tunneling. If you would try to do this is where I'm saying the parallel package itself can do this thing too. It's very, very tedious and you need sysadmin rights and things. First of all, you need to know your public IP number, because you have to tell the workers who you are so they can connect back to you. And in order for them to connect back to you, you have to open up your incoming firewall and configure port forwarding. And this is like what most people can't do. You either don't have the right, or it's like super tedious. This approach works anywhere. You can sit in a coffee shop and it will SSH into those machines, and they will connect back to you for something called reverse tunneling, fully automatic. Okay. So that's the parallel package. It's also part of the Futureverse, but it doesn't use any futures. So if you use other type of parallelization, you can just use this one. Okay. Question. When using plan cluster, does the data we use for our function get uploaded to those clusters? Yes. So back to when we, whatever we do, where are we here? These machines are installed. But they don't know about this function, because that's a function we defined locally. But the future framework will take this function and serialize it, pack it up, and send it over to those machines. And it will also send over the data. So if you have a lot of data or big data objects, then that will introduce an overhead, and it can be significant. And some of these MapReduce packages, FutureApply for, they are very good at splitting up the data, so it doesn't send over everything. It only sends over what it needs to send over. But yeah, it's true. If you have very large data, it might not be worth sending it to another machine. It might be faster to do it locally. Sure. I have the feedback here. It's if you wonder if I get like a bit confused, I actually get it playing in my ear every time I get a comment here, but it's very useful for me to see. Okay, so there are other parallel backends too. There's the future.calr, which parallelizes locally using the calr package. So it works very similar to the multi-session, and you can call it like this, calr, and this definition here, and that also works on all machines. The advantage with this is that it works around the limitation that R has. I would say it's a very silly limitation, but we limit it to 125 connections in R. So you can only have 125 files, for instance, open, or connections to parallel workers open at the same time. And then after that, R will say, sorry, I don't have any more slots to hold those connections. And this was like a limit that didn't matter when we had like 8, 16, 32 cores. But now people are running machines with 128 cores, 196 cores, and even like, I think 384 cores. And if you would try to do that I mean, I can actually show what that looks like. If I say trying to do 250 cores, we get an error because the parallel package will say, hey, I can only give you 124, so I won't even try to do this, which is a bummer. But if we would do this, it works. I won't do that now. I want to spin off 250 workers here. So that's a very great advantage with the CallR package. If you run into that limitations, you can use that. Okay, someone is asking about what happens if it ends in an error. We will get to that soon, or in a while. But yep, it's okay. And then there is the future.batch tools. It allows you to, if you have a high performance compute cluster, to take your, so since, let's see how many we were. Okay, 20 people had access to compute clusters. And you might know about the job scheduler. So you can write a bash script, and you can submit that bash script to the job scheduler queue, and you can submit many different versions of that job script, and they will queue up. And if there is together with other users, and if there is a computer available, or a few slots on the computer available, they will eventually run and then return to you. You can do this from within R using this plan batch tools. And this is a case where we have a Slurm scheduler. So when you create a future, that future will become a job on the job scheduler. Start R, run the calculation, save the files, results to file, and then later when you ask for it, it will load it back to your R session. So you, of course, there's a lot of more overhead in this because you have to queue, you have to wait for things. So don't do this for things that needs like snappy answers. This is more like for large, long-running futures, or a lot of them. So you can do a lot of throughput, because this way you can run maybe 1,000 futures in parallel at the same time. Question is, does it work with task spooler? This is the first time I ever heard about that. I assume that's an HPC environment or a job scheduler. But so the answer should be no, because I don't think so. This is if batch tools can support it, because it's the batch tool package under the hood. But if batch tool doesn't support, you can actually create your own templates. So it's possible to get things working. And then it would be possible to get it working here too, through a custom template. Okay. So designing philosophy, the key here is when I want to bring home to is if you're a package developer, you are the one who decides what to parallelize. You're the one that decides where should I use future, or future lapply, or future map, or for each. What you shouldn't really do is to say how you parallelize. Leave that to the end user. Because again, you might think you have a fast machine with 96 cores, so you're happy with the multi-session. But if you do genome analysis, someone said, hey, I want to scale this out to 20 machines. And if you hard code something inside your function, then you're preventing those users for scaling it up. So avoid calling plan inside of your functions. Okay, we should definitely have a break. But, let me show this just as a teaser. I'm going to run a ggplot on remote machine. instead of calling this locally, I'm now calling the ggplot remotely. Okay, let's see if it's done. Don't have to do it, but yeah, it's done because it's a very fast thing. Let's take this value back. So now, someone asked, so this is what's needed to be sent over here to this remote machine are a few things. The ggplot function, and this is actually not needed because ggplot package is already installed, so it won't send it over, but it needs to send over mpg, which is a object sitting locally here. And it creates this thing and runs it, and then the value back is a ggplot object, which I ask for. So if I now look at this object, let me open it in the window because it's small. Oh, okay. I can't multitask here. Okay, it opened here, as you can see. That's the best you get on this small screen. But that's pretty cool. It's actually creating an object on the other end and send it back, and you plot it locally. Okay, stop sharing. Find my way back to you guys. Oh, there you are. Okay. Okay, so let's have a break. We 1.5 hours in here, and let's come back in 10 minutes. So on my clock, it's going to be 8:47. Okay, hi again, everyone. I guess you guys can take breaks when I'm talking, but I need breaks too. Can someone confirm that I'm live again?
You're live. You're live.
Beautiful. Thanks. Hi, Susan.
Hi.
Hey. Now I can see there's see the thread. Okay, so I'm going to start my screen share again. There we go. Okay, let's talk about the MapReduce API. Because now you know a lot of details what's going on and why things works the way they do under the hood. So, as I said, the three atomic building blocks: the future, resolved to check if something is done, and then get the value. With those, you can build up a lot of things. And you can actually use them as is with this lapply, as we saw, things yourself. But you can also optimize it more, like splitting data up in chunks and iterate things in different ways. So our package is called future.apply and fur that are directly dedicated to do this, and they build on top of these three functions and nothing else. Then there's the do future package that does the same as a plugin to for each. And again, it's only using the function future, resolved, and value. And since Plier internally use for each, you can also use the future framework on Plier. And same with Biaxy Parallel, you can use for each plugin, which means we can use futures. And what I want to convey here is these are all siblings. Their goals are all the same. It's so-called MapReduce. You have something, a vector of something input or a matrix or data frame, and you want to map that to a function and then calculate the things, and then you reduce it to some results. So they are no better or worse than the others. So that's key thing. So when people say, should I use for each for parallelization, or should I use fur for parallelization, or Plier or Biaxy Parallel or future apply, does not matter. Use the one you like to use. They're equally fast, equally slow. They have the same limitation and the same benefits. I want to say this, like, when you use these for each Plier and Biaxy Parallel, I say use the do future backend, because then you're going to have more benefits. We will get to those later. Okay. So if you look at base R, there are set of function. We know some of them, like apply. There is a one called buy. Some people use it. Some people never heard of them. E-apply, I never used it. L-apply is a very common one. Map is fairly common, which is a nice, it's just a fancy wrapper on top of something called M-apply, which is multi-apply. Replicate is you want to do exactly the same thing many times. That's like when you do bootstrapping and things. You can use replicate. S-apply is for vectorized version, is an alternative to L-apply. T-apply, V-apply is well-known too. So the future.apply package implements each of these, so you can parallelize with future. So if your code has an L-apply and you say, oh, this takes a long time, I think it's worth parallelizing it, just replace that by prepending it with this, and it should work. If you have an M-apply, you can do the same thing, and so on. Okay. And I here want to show also how they all siblings. So let's consider this example. We have another slow function now, slow square root. Find my way back to Studio. I have so many things going on here now. So probably lots of workers running in the background. Let's do multi-process here. It doesn't exist anymore. It's deprecated. Multi-session. Okay, there we go. So now let's define this function, slow square root. As you say, it calculates the square root, but it's emulating slowness. So if I take 2, it will take a second. Okay. So if we use lapply on a vector x, capital X, this will save time. I won't paste this entire studio, but it's going to take 10 seconds and return a list with the values, 10 values. And future lapply, we can do this. Now I already did the multi-session thing, so I can do this. It works. And we get the same results. So it's plug and play, replaceable. So here's a challenging question. If we have 10 elements going in and 4 workers, you can think about how long this will take to finish. Since each of them takes 10 tasks, that takes a second each, and each worker so we can split them up. We can split them up in 2.5 tasks. So there will be several workers with 2 tasks each, but there will be 2 workers with 3 tasks. So those 2 workers that will need 3 tasks, they are the one that will take the longest. So it will take 3 seconds to finish if we use 4 workers. Okay. So that's a plug and play replaceable with lapply. So now if we look at fur, we can use fur to achieve exactly the same thing, and it looks the same. It's called future_map. Same results. And this is more important. That might not be surprising, but for each, it's doing the same thing. So use for each. We have to tell for each we want to use the future framework. That's what we use with this. Now, whenever we do for each with this do par, it's going to go through the future framework under the hood. Again, you don't have to worry about that. It's just happening, but same result. So very important here, because this is a very common misconception. For each, return something. So you always want to have something like this. It's not a for loop. If we have time, I will show that at the very end, but it's not a for loop. It looks like a for loop, but it's not a for loop. It's just like lapply and map, etc. So remember that. Here is how we can use plier. I'm sure there are like plier users out there still, although it's supposed to be no longer under development. You can use all the plier function and you say dot parallel equal to true, and as long as you say do future here, lapply will go through for each for this and into the future framework and parallelize for the future framework. And same results. IC parallel, you can tell it to use do par, which means use for each. There's a lot of setup here to tell each step to use something, but this is how we have to do. And then you can use the BP lapply of the IC parallel, and that will now also parallelize through the future framework. Okay. Let's look at some non-future alternatives here. Of course, I just want to mention that you have seen do parallel, register do parallel. That will of course work here too, but we will later see why it's beneficial to use the do future instead. But the non-future alternatives, this is the most common one that people see. We can use the parallel package, and we can say use the MCL apply, and we say use 4 cores by default. You can also specify that as an argument, but it's also always nicer not to have to clutter your code with configuration, how many workers you do. So I prefer to use an option if I had to use this. But this was also then run in parallel and return the same results. So that's, and then if we use the very tedious one, because this one doesn't work on Windows. And think about this if you're on Mac and Linux. So if you use this for your code, you're leaving Windows users out in the cold, or you're actually leaving them to run sequentially, because that's what MCL apply do on Windows. So Windows users, if you don't use the future framework, which of course I say you should, but if you decide not to do it, this is how you have to achieve the same thing. Load a package, set up a cluster for workers. You say, this is my cluster I want to use. Alternatively, you can pass the cluster argument in the call. But then you also need to say, export this function, because the workers don't know about this function until you export it. And then finally you can call this. So the benefit of the future framework, you don't have to do this exporting. It's just automatically happening in the background. Okay, let's do one more of these examples. I'm going to skip the v-apply because it's quite similar to. Let's do that one. It's and skip the. So v-apply is like l-apply, but you can get, instead of getting a list, you can get a vector back. So it's a vector apply. And what you pass the input, the function you want to apply to each element in this. But you also then say a template here. The default template is to return a numeric or real number, not a number. In case something would fail or doesn't exist, then there would be an NA, but you have to specify a template. And that will now trigger it to return a numeric vector where the values are accessible as a vector instead of a list. And of course, the future.apply package has a one-to-one mapping, so you just replace the above code by prepending this and you get the same results. Per has from per the map, and now say return a double, and you get the same results. For each, it looks very similar to the lapply call, but now we add combine. So it's saying like combine the values using the C operator. That's this one. It's basically saying, instead of getting the results element like this, oops, yeah. If the result would be like this, it now gives you this. So that's how the combine works. So for each is very powerful how you iterate and combine things at the end. And then again, plier has its version. It's saying take a list as input, our X, and an array as output back. There is a question, what are the available objects from the user session in parallelized processes? So in the future framework, the future framework tries to export only the things that are needed. Try to avoid having like extra load and cargo passed over to the workers. and that's taken care of by the globals package. So this should be taken care of automatically, and the different fur and future apply and do future does this also. It doesn't send over a big object if you're only going to a big data frame if you're only going to calculate something on a few of the rows. So then it sends out the chunk that it needs to calculate. There are things that has to be still thought about here. But we can discuss this at the end. But most of the time you don't have to worry about that. The non-future alternatives to what for this vector apply. You don't have that in parallel with the MCL. You only have MCL apply here, so you have to do your MCL apply, and then you have to vectorize it yourself afterwards. Similar with a cluster approach with parallel. Export, and then you have to call Parallelization, and then you have to unlist. So that's unfortunate. They could have implemented like a Parv apply and an MCV apply, but it's more low level, so we have to do things ourselves. I'm going to skip mapply, multi-apply, but it allows you to pass two vectors, iterate over two vectors and pass those as elements and calculate things like that. And there are alternatives for that in future apply, of course, and then for you can do it with for each and things. But it becomes quite tedious if you want to use other things. Actually, there is an MCL apply in the parallel package. There is no par M apply. Okay, so point there is that all these for each, future apply, for applier, etc. You can do the same thing in those slightly different ways, but they're equally fast, equally efficient. And the FAR package was done by Davis Vaughan. He implemented this future version of FAR. So there we have a lot of map reduce functions, and there's a corresponding future version of each of them. So if you find you need to parallelize an iWalk, you can do that by using a future iWalk. Pretty cool, I think. Okay, so now to the question that someone asks, so what about errors and stuff? This is where future framework provides the most benefits, I would say, or another area. So I would say with the when you parallelize with the future framework, and this is not true for other frameworks, errors works the same way as if you do sequentially. Warnings work the same way. Messages, actually any condition objects, if you know about condition handling in R, works the same way. And also standard output, things that are printed and cat and str works the same way as if you would run it sequentially. And I'm going to show you what I mean by this. But what actually happens is that when we look at errors, if there's an error, if your future expression generates an error, it will happen on the parallel worker end. And that's detected by the future framework. And that error will be transferred back to you and resignal as if the error was actually happening on your local machine. So let's consider the square root function here. If we call square root of -1, r will return not a number, and it will also produce a warning, and that's good. But say you want to be more strict. We want to actually get an error here. There are options in R that can turn warnings into errors, but let's say we want to have a function that produces an error for negative numbers. So we could create a function called strict square root, and the first thing it will check if the input is less than 1. So this assumes only taking a single value in. If you had to do like a vector, you have to do something more here, but this is only one scalar. So if the value is less than 1, it will give an informative error message. You can't do that and say what value you used. Otherwise, it will calculate the square root. So if you call this with strict underscore square root -1, we're going to get an error telling us about the mistake. If we do this with a future, this actually works too. And now I should copy this over here. Do this. Now, nothing happened, of course, because this was evaluated in the background. We haven't asked anything about the future yet. It might be done or not might be done. But the thing is, it's impossible to give an error here because it's just sending this off and returns. And the error might happen in 2 minutes. So, and it won't just pop up here. And here's business as usual. But now if you ask for the value, it's the value for this. Now we get the error. And it's exactly the same as you would call it locally. More details later, but the thing with this, now you can handle this thing. So for those who don't know, there is something called exception handling in R. You can use a try-catch function. So say you don't, for some of your calculations, you might get an error. So, and we don't really know if we get an error. If now we know it's going to happen because we passed -1, but sometimes we don't know the value passed in. We can, when we get the value, we can use try catch, which is part of R, and say if there is an error, go into this function, create a message, an error occurred, and append the actual error message, and then return NA numeric. So if we do this, so remember, this is actually, if I do this, we have an error. And by the way, if I call value all the time, the error is re-signaled every time we call value. It's not very common that you call value many times, but that's the design decision. So if we do this now, it's going to be an error. It's going to be caught here. We're going to see a message, and the value will be returned here, NA real, and that's going to be assigned to this instead of this. If there would be no error, V would get the non-error version. Say we get the message, and we look at the V, NA. So let's try it with slow square 2. I do the same thing here. We don't get an error, and we get the value, and V is 2. So that means the future framework exception handling works the same way as if you do it sequentially. So remember that the error is signaled when you do value, not when you create the future. And this also carry over to our MapReduce frameworks functions. So of course, if you do this, in R, sequentially, we're going to get an error saying one of the values is negative because the first element was negative here. This carries over to the future framework as is. Also get an error. And future for behaves the same way. So take-home message here is like you can treat errors the same way as when you run sequentially. I have, this is like in appendix, I've prepared how this doesn't work in other things. If you use Parallelization, you actually get it detects the error, but you actually get a modified error and you lose information on the original error. MCL apply is actually not handling errors, it's only producing warnings, and it's up to you to handle that. If we have time at the end, we can look at those. Okay, let's see. There was a question. Okay, does it stop everything at the first error? So that's a good point. Say we call something, it takes a long time. It's even if 1 out of 100 elements, only 1 out of 100 gives an error, all the others will continue processing and you will get an error and you lose the information on the results. And that's exactly how lapply works. So by design, the information will be lost also with future lapply. There is a free feature request. It's like, hey, can we have an option to at least keep the other results? And I agree with that, but that probably have to go in another package because this future apply package, and I think FUR is the same philosophy. It should be a one-to-one mapping. If we start adding other behaviors, it's a different story. But there's nothing preventing us from implementing other fancy solutions. To the question, does it stop the other workers from running as soon as it detects one of them gives an error? It can't, because we don't have a concept of stopping workers at the moment. That's on the roadmap, but it's a very complicated task to stop a worker. You can do it on a local machine, but if you're running remotely, it might be very complicated, or a job scheduler. So this is something we want to do, but we have to be very careful implementing it. So it's going to take quite a while before that is. So it can't stop. Another way for this question about stopping, someone asked about this, and it's actually turned out it was an oversight. It should stop submitting new futures if it detects the future, an error. But it turns out it actually doesn't do that, so it's a bug now. So if it do -1 first, if it runs on a single, say it can run -1 and 0 first, and then these two has to wait for a worker to be available, it should stop and not sending those over. But that will be fixed at some point. Hopefully that answered your question. Perfect. And for those who don't, who are watching the video later, when I say perfect like that, that means the person responded in comments and said thank you. Okay, what about warnings? And this is the cool thing. So other parallel frameworks do handle errors in one way or the other, but we lose some of the information. But none of them do warnings. So if we do, say, the log function, that produces a warning here too. It's going to give you a warning that the -1 is producing not the number. Future framework handles this. And they catch the warnings on the parallel worker wraps them up and sends them back to you together with the values, and then signals them to you. The term signal is like producing, generating in the R terms. So when you call the value, each time you call it, there will be, oops, I can't zoom in without losing. When you call value, you get the value, but you also get any errors, warnings, and output here. So that warning will be signaled here. And if you don't want it, the warning to be signaled, you can suppress it. You do this, and you can wrap it in the suppress warnings. And suppress warning is part of the regular R. So you can do that on a future or anything. So let me show you. If I do log minus one, you can do suppress warning log minus one. You see, we're skipping the warning. And that means you can do really fancy things if you, with warnings too. You can use something called with calling handlers, and also now these days global calling handlers. So you can turn warnings into errors, you can tweak them, you can clarify them, you can print them out in red, you can print them out in a printer, whatever, with calling handlers. And of course, with the map produce APIs, you get the same thing. So if we do this, we're getting a warning. And we can suppress the warning, we can handle it. And we still get the values. And again, take-home message here is it's the same, exact same behavior as if you do a lapply. And as I mentioned, none of the other parallel frameworks do this. Warnings are just lost. They end up in the void. Okay, messages. Messages are very similar to warnings. This is when we call the message function, and since we use this so often, people might not be aware of it, and I don't think about it much myself either, but it's actually what happens is it takes your string that you create and wraps it up in something called a condition object of class message. It sends it through the R's condition handling system. And that condition handling system can capture errors, warnings, messages, and you can do whatever you want with them. And if you don't intercept them on the way, they will eventually bubble up all the way up and be printed to you as an end user. But it goes through back channels, I call them, which is the condition system. So conditions are really cool. And I said, like the 2020s, this decade is like where I think we're going to see a lot of usage of them. So let's do this one too. So if we create a future, this is like a future that has a more complicated expression inside. It's not just calling a function. First, it takes the first 8 letters in the alphabet, assign it to the Z variable, prints the message, and then it ends by returning this one. That's the value we're going to get out of it. So if I create this future, I now call value. Oops, if I do value on this, what will happen is that value relays any warnings, errors, and messages first, and then you get the values. If I store the value in Y, we're going to get the message. And we're going to get the message every time we call it, and then the value is here. Do messages always get printed in the same order as they would do for sequential? Yes, that's a very good question. Because if that's the decision. Of course, you could create, say, parallelize and don't care about the order, but that's a design decision we made in future.apply with fur and do future, that messages would always come in the same order as we put them. So if we do this now, it might even be coming later here. Yeah, here is an example. I take input x 1 to 3, and I now create a function that outputs this message. I don't really care about the value, but we can see the output. It will output them 1, 2, 3, regardless how you parallelize and which one would finish first. So if I would do, let's try to make them finish in the opposite order here. Like the sleep, and the sleep will be 1, 10 over x. So first one will take 10 seconds, and the last one will take 3 seconds. Okay, let's speed it up a little bit, 5 seconds. One, two, three, four. So there's a lot of orchestration. It's like, yep, that's awesome. Yeah, it is. It's on purpose, because the point is, like, lapply and future lapply should be replaceable. Okay. Now there's another thing called standard output, and if you don't know what that term is, it's output, but message is also output, warning is also. Standard output is a term in operating systems where plain text is sent. There is something called standard error. That's actually where the message eventually ends up. And if you have messages to users, progress bars, and things like that should go to the standard error, which they do, because we send them through the message command, or all different progress bars, they also output to standard error. When you send to cat and print and do string, they do standard output. And you might have seen this. This is, if you think about vignettes. Vignettes, if you do print, the vignettes are designed to capture this output, but they ignore messages unless you tell the chunk in knitter to say report on the messages too. But that's the way how we can run vignettes. So the output from print and cat that we want to see in our final report will be part of a report. But progress bars and things that runs while we're waiting for the vignette or the report to produce, that doesn't end up inside the vignette. So they're two different output streams. So same here. This is, of course, an example to do the same thing, but we're now using cat instead of message. And this doesn't use any condition system. This just sends it directly to the standard output. And the future framework captures that too. It's going to look very similar. Every time we call, it outputs whatever it captured here. Again, this is running. It might actually still be running in a remote machine or in parallel on my computer. Okay. And this thing, standard output, we can capture with this if we want to. So we can do things like this. Instead of, when we call this, it outputs to the terminal. We say capture it into a variable called standard output. And now that's a string like this. And I can already tell you now, if you try to do that with other parallel backends, you're going to get nothing. It's empty. Because it's only the Future framework that captures standard output. We don't have a suppress output in R, surprisingly, but you can use this trick. You can say capture output and send it to the null file. That's sending it to the void. It just discard it immediately. So that's how you can silence output. And again, similar to the question before, standard output is also guaranteed to be outputted on your machine in order, regardless how long things takes. Okay, so we know that errors, warnings, messages, any type of conditions actually are relayed. I call it relayed, captured, and then resignaled. And this is also for standard output. So here is an example. So here's the one thing there is no way to solve, which messes a little bit with the order. I'm going to explain. Do this, first send hello world, a new line, then sends it a message, hi there. Message always add a new line by default. Then it creates a warning. Then it creates another message. Calculate log of a string, which produces another warning. And then finally creates a message. Actually, I'm surprised. So this works. So we get the hello world. Hi there, please wait. We see the warnings are captured in signal, and that happens if warnings are added to the end. So that's this warning. Log, that gives an error actually. So we get an error here, and this one we never reach because the error causes it to interrupt. But this is how you would get it in regular R2. So the one I wanted to say, if we do something like this, oops, cat hello, message, hi there, cat world, and then return 42. This is the one thing that happened. You see that hello world comes first and then hi there. And this is because this is standard output and it's captured. And this is a message. And there's no way, we can only capture standard output as one big chunk. There's no time information. In conditions, they come in order. But standard output comes in a chunk and we capture that. So we can't get it to say, hello, hi there, world. If someone out there knows a way to do this, we'd be happy to add that feature. So the rule is like standard output comes first and then all the conditions. Okay. Okay, odds and ends. What about standard error? R has, you can send things directly to standard error. Okay, let's go back to that question. Why is 42 not considered a standard error? Okay, let me do that again. Oops. So I'm not that savvy with, I do this, hello, 42. So 42 is not, that's the value. It's not output it to standard error. That would be if I did something like this. I have to do this, or print, something like that. But basically, when we do this, it's just like doing return 42. I don't know if this clarifies it. So when I do for value f here, I take them like this. I only see the output, but 42 is part of the value. So maybe if I do this, it would look like it's standard output. This is the standard output, and then the R prompt may print this one for us. Okay, good. That clarified it. Okay, so standard errors. So you can send things to standard error in R, which is fine, but you can also capture it. And there's the default is type equal to output. That captures standard output. If you do type equal to message, you capture standard error. But you don't want to do this because it's only one person, one package, one function is allowed to do this. And if there are nested calls to this, it's the last one that trumps previous ones. So if I have a function that captures this, and then my function calls something else, and all of a sudden this something else get updated on CRAN and start using capture standard error too, they will steal everything from me, which is fine. But when that function returns, my function will should get the capture back, but it doesn't. So it's not a safe thing to do. This is a very technical thing. You very rarely need to do this. I've seen some packages using it, and they don't know about this limitation in R, but it's very rare. So, but if you wondered, that's how it is. And by the way, this message has nothing to do with the function called message. Okay. Okay. I don't know. Should we? Are there more questions here around this? No questions. Okay, let's see. Let me just see if I have. Okay. Oops. I'm not really good at multitasking screens here. Okay. So progress bars. I should say progress updates. I try to avoid using progress bars because it's very limiting in the sense that it's visual. It often indicate a terminal progress bar, sometimes a shiny one, but progress can be reported in many different ways. So I try to say progress updates. And this has been an ask from the beginning of 2016 or 15. How do I do progress updates reporting in parallelization? And I've been punting and holding back on that for a long time because I wanted to solve it not just a quick and simple way, but for a very generic way. And so the easiest one would be that if you imagine future apply, if you have 4 parallel workers and you do a future lapply of 100 elements, what future lapply would do, I haven't explained this, but that's how it does by default. It takes those 100 elements and chunks them up in 4 pieces of equal size. So that would be 25 pieces per chunk. And each chunk will become a future, and that future will end up on a worker. So there will be 4 futures running in the background, one per worker. And the most simple solution for progress bar update would be when the results come back, then you update your progress report. So if you have a progress bar that says 0 to 100%, as soon as one of the future would come back with a value, it will increase 25%, and another 25. But you have no idea what happens while it's running. So if these 4 chunks takes, I mean, this is not unusual. It might take like 2 hours. You won't get a progress update every 2 hours. So that is unfortunate. So instead, we tried to come up with a model where we can report progress update live from the parallel workers. And again, this should work when you run sequentially or parallelize locally or on machines in your office or across the world. So, excuse me. So you imagine you need a way of communicating this thing, informational progress, in the background while things are running. And this is where progressor package comes in. It actually was created as a proof of concept. It wasn't meant to take off because we have the progress package, which is an awesome package, which is now superseded by the CLI or CLI package. So theoretically, we might be able to use those, but it needs other updates. So I created a progressive package as a proof of concept, and that can be a wrapper around those packages. But it turned out to be successful, and people started using it, so it became a real package on Crown in 2019. So this is how you use it. Now imagine our slow function, slow square here. This is another one version. This actually takes a vector as input, and it uses a lapply over each of the elements and calculates square root. And there's this sleep to emulate slowness. What's new here is this set of saying, before we create this lapply here, we want to create a progressor object. And we're saying we just want to progress along this vector. So this is saying if x is 100, this will create a progressor that has 100 steps. If it's 10, it's going to be 10 steps. And you get a handle to it. We call it p. We can call it whatever, but I like p. It's short. And every time you make progress, you just call this function. And this will then signal, and this is actually signal a progress condition object. And that's all it does. And then it's up to us to somehow pass that along in parallel processing and listen to it and listen to those signals and create a progress report, maybe a progress bar, for instance. But as a programmer, all you have to do is this. So there's nothing about what it should look like, or it's just signaling like I made progress. Okay. So if we use this here. Now see, I'm not using an lapply, I'm using a regular lapply, so there's no parallelization. I should load progressor here. We don't have to do that at this point yet, but if I do square root 1 to 10, or let's say 1 to 30, This is now going to take 3 seconds. Okay, where's the progress bar? It's not there because we never said we wanted to do anything and listen to it. And we can do that by with this function, handlers, and we say global equal to true. This comes from, technically this comes from like a global condition handler. This is like report, it captured globally. So if I do this again now, let me start up from the beginning. Here's the progress bar. And we can turn it off. We almost recognize this from the future framework too. This is something the end user choose to say, I want to see progress or not. As a developer, the code they call is still the same. So there's no like progress equal to true and things like that. Just have a global setting to do that. And so the developer, all you have to focus on, okay, I have a function, it might take some time, so let's signal progress updates. That's all you have to think about. Okay. So now we're talking about parallelization here in this tutorial. All we need to do is now replace the lapply with the future lapply. And here I'm doing it using this, so I don't even have to load the package. So let's do that. Copying it. That works. Okay. Now I have that function here. Let's start with a sequential. Okay, and here we go. Let's turn on the, I want to see progress, care about it. And here we go. So it works the same way because future lapply is, you can, and lapply are substitutionable. Okay, and then of course, now this is the cool thing. If we do workers 4, might be too fast here to see it, but should see it go faster. Let's do 100. If I try to do 8, it should be twice the fast. And if I do 2, yep, super cool. Yeah, I'm proud of it. It's worked. So there's a lot of things going on here, but it's as a end user, you don't have to worry about it. It works the same. As a developer, on using futures, it's works the same. Okay. So it just works. There was a question about I don't understand sprint. Okay, sorry about that. Sprint is something from C programming, but if you do this, that's, if you've seen glue, those who've seen glue, this would be the glue version of it. Let's see, I don't know how you do that actually. Hi, maybe. Anyway, it's a similar thing. It's a format string. Okay, why do I need to specify message? Okay. Oh, I forgot to say that. You don't have to. We could have used the regular P here. I'm going to get to that later. So what you can do, this is the simplest form, just P. You can also send along a message. Okay, so, but we don't see it when we didn't see it when we called here, right? See, we don't see any X equal something here. And that's because the progress handler we're using doesn't support that. However, if we turn handlers, if we turn into the handler from the progress package, it's capable of reporting on messages too. So let's see what happens here. X equal here. And so again, it signals a step forward, and is also a message per progress. And then the end user can decide how they want to report on that. Okay. So let's see. And of course, this, as I said, this works if you parallelize across the world. And actually how that works is that when the future framework on our computer keeps asking the other machine, are you done or not? Then it takes the opportunity to bring over those future or those progress updates in that call. So there is a little bit of delay. If you don't ask the future work or anything, you just launch it, there will be no progress reported. But if you call result or value, you will get those coming in a near live fashion. Question, does the progress bar method exist for each? It does. And the reason is, as long as you use the future. Now, that was a double colon. Now, by doing this, you tell for each that please send anything to the for each framework. And as I mentioned before, early on, it's like future, apply, for each, they're all the same, they're doing the same thing. They're just different ways of iterating over objects. So if I do this, say 1 to 100, it's going to be tricky, but I can't do it live here. I have to replace what I want to show you. Let's see. My Emacs. For each, probably too small for you to see. Bear with me, I will paste it in soon. Okay, so let's look at this. Slow square root of 2. So this looks very similar, but I just replaced the future lapply with this. Otherwise, it's the same. And I did this too. So now for each, or actually this one, will make sure it sends everything to the future framework. Okay, so let's see if what happens we do slow square 2, 1 to 100. See my fingers, it works. Okay, so again, pick the for each, whatever you want for, will work the same. Stay with the one you prefer. Okay. Then, just for the progressor package, we can choose to not, this is where I'm trying to do a demo here. And so actually, I'm going to run this in the terminal because the deeper package turns out it has some issues with RStudio in some cases. So I'm going to do I already have this preloaded now, so we have the slow square here. Actually, I don't have the parallel version of it. Bear with me. Come back to this. Now I have the parallel of the future apply version here. I've loaded the packages. So if I do a slow square 1 to 10, you won't see anything because we have not created, we haven't told it to use reporting on progress updates. With this, oops, terminal too narrow. Actually, option with 40. Should pick this up automatically, but it didn't. Okay, so there we go. Now let's see if I can get volume up. So if I now do handlers beeper, beeper, of course. Okay, and let's do a bunch of them. Now let me know in the text if you can hear anything. I took off my headset. Yes, okay. Catching. So that's a way to produce progress, and for those who don't like the visual feedback. And we can combine them, of course, if you want to have both. Let's do a quicker one. I actually do not know why it didn't end up with 100% there. That was a glitch. It should have done. Probably a bug then. Okay. Okay, and then we can do very fine-tuning, because we can do every setting that the progress package has with format, spinners, total, estimated time to arrival. We can change beeper to use the Wilhelm scream at the end. If you don't know what that is, it's a very famous scream. They used in a lot of movies. This is one. Go read up on it. It's a fascinating story, how it ends up in a lot of movies. Okay. And then if we use RStudio, we actually use the progress handler in RStudio. So now if you pay attention to what's going on up here, see this one. So the philosophy here is like, end user of your tool decides they want to listen to progress or not, and they can also control how to view it. Or so it's a separation between developer and user, just like in the future framework. We're at 10 o'clock. I'm curious. Most of you are still hanging around here, 36 people. That's good. So, any questions more on this? Okay. Okay. Thank you for kind words. I wonder if you have any plans to make the globals package handle pointers so that reticular and Python object can be automatically exported to workers, for instance. Can we save that later? But it's, yeah, there is work on that. It's this is related to, I have a section on that at the end, that some objects cannot be sent to, they only exist in the R session where they created. And it's a complicated things, but there are some thoughts to moving forward. Might not be possible to fully automate it, but yeah, let's get to that later. Sorry, I wasn't able to reproduce the progress example for each. Could you share the code? Yes, and it's actually, if you go to the Futureverse.org, it has all the examples here. And there should be a search for each. There's for each sequential and for each parallel. So here is an example you can start playing with. But I can also share the other one later. Yes. Okay. Hey, let's. I want to have another short break, not 10 minutes maybe, but 5 minutes soon. But let's. I mean, there's a lot of technical details here, but let's look at Mandelbrot set demo. It's always complicated to do instructions and tutorials of parallelization because they need to be fast enough to run in interactive mode to demo them. But when they're fast enough to, you might not appreciate the parallelization. And so it's hard to come up. That's why I have this like slow sum and slow square dummy toy examples. But here's another one that 7 years ago on an old computer, it will made sense. But even here, I had to emulate slowness. But so Mandelbrot are these fractals, which are really, really beautiful. And it's based on mathematics. And this, what we see here is the plane of the real axis horizontally and the imaginary axis on the y-axis. And by imaginary, for those who are not into math, that's most of us knows numbers along the real axis, minus something to positive something. But you can also have things on the imaginary axis, which stems from taking square root of -1, which I said doesn't work, but it actually does if you define it in math. So moving this direction, we actually have large imaginary numbers and small negative or large negative numbers here. So it's and here in the middle is 0, 0. The Mandelbrot set is, these are, the Mandelbrot set is actually the black here. This is like when you start your value, if I start the value 0, 0, that's the origin, and I put that in the Mandelbrot function, I can ask, do you belong to Mandelbrot or not? And that is a function, that's a question that is hard to ask. You don't really know. For some numbers, it's very quick to say we know it. And that's the one that are black here. They will, in this algorithm in question, they will converge very quickly. So all these like converge very quickly to an answer saying, yes, I'm part of it. Also out here, the red ones, they are diverging very quickly and saying, I'm not part of the Mandelbrot set. But then on the border, there are numbers that oscillate between, want to say like, I'm part of it. No, I'm not part of it. And you have to run some of them like very, very, very long time to get an answer. Or you might not even get an answer because you have to you don't have numerical precision enough to say answered. But the colors here are how fast they answered. So black is like very quick, like I am part of the Mandelbrot. Red is like very quick, I'm not part of it. But the green and yellow color scale here is like after like 1,000 iterations, it said, yes, I'm part of it. Then we colored green. Or after 10,000 iterations, it said, yes, I'm part of it. Then we colored yellow. Okay, so that's short story how that's generated. It's a fascinating thing that's more than 100 years old. So there's a demo in the future package, but I also have a demo in the progressive package which illustrate this better. It's going to look kind of funny if we run it in the plot window on RStudio. So if you do it in RStudio, I recommend you to do X11. Open up a separate window. Actually opens up in a different screen on mine. So I'm going to use our terminal instead, where it will open a window. Okay, so let's have pasted this one. So this is just saying there are 3 different predefined regions. So I'm just saying plot the first one here. And the demo. You can run this demo and you tell it don't stop and ask to open plots and stuff, just run it. And I'm going to run it sequentially. Oops, it's open. It's still in the wrong window. Can you see this window I pulled over here now? I moved my plot window over. Can someone confirm they can see it? Yes, good, thank you. Okay, so now you see it's plotting and it's reporting on progress here as well. And now it looks funny because I pulled it over here. It shouldn't be. What this does, I decided to split up the calculation of this, the big Mandelbrot window, into a 5x5 tile set, and I calculate each tile separately. And I do emulate a delay here, so it's faster than this actually. But you can see it like sequentially. It starts like finishing up tile by tile, and then it reports when it's done. Each tile is done. And you can see also that the tiles are not finished in order, which makes sense because some of them are like very fast and some of like have lots of details, so they take a longer time. Whoa. You probably didn't hear that, but I had deeper reporting on me. Okay. Now let's run the same thing in parallel. Workers. Where are we opening? Another window opening. Oh no, I didn't start anything. There we go. Window open again on the wrong place, but now you should see this runs faster. So running in parallel, reporting on progress, everything for the future system. Okay. Pretty neat, eh? By example, but works. Then we can do, there are other beautiful pictures we can do here. Oops. There's another region where we zoom in somewhere on this, along this edge, and that's why we get much more colors. So, okay. We have a 5-minute break here. And we get back in 5 minutes. Okay. Thank you. So my clock is 10:08, so 10:13. See you in a bit. Oops, sorry. I've been speaking into without voice here. Now you can hear me, probably, I hope. Okay, I see there's a countdown, 15 minutes left of the session, and I understand if people need to leave before that, but I also assume that we're going to get kicked out by then. So let's continue quickly. So that's the quick summary here. This is like, why should I use futures and not futures? Okay. This is a bit unfortunate tweak. Okay, so basically, future framework or for each bias parallel when using the futures, take care of exception handling, warning, messages, standard output. Something we won't really cover today is parallel random number generation, which is super important if you do statistics and reproducible research and things. That's done with the future framework. I say for each has a special way of doing it. Bias parallel can do it. I would say it's a little bit tedious to do it in the sense that there's a risk people skip doing it. One thing that is unique to the future framework is that it will actually warn you if you forget to do it the right way. So it will nag you and saying, hey, you seem to be used random numbers here, you didn't tell me. So please fix that. And the reason why it doesn't do it automatically is because there's an overhead. And we saw progress updates can be done very well. Also, this thing that's kind of unique to, thank you, I forgot to share. I am not sharing something. Thanks for saying that. This is what I meant to share. I hope I'm sharing now. Yeah, I see the same thing basically, regardless. Anyway, so here's a summary. Thanks for letting me know. So future framework here ticks off a lot of boxes: exception handling, parallel randomization, progress bars. And it also ticks off you can run single expression parallelization. That's what we saw in the beginning. You can call future and value. The only other thing that can do that is basically MC parallel and MC collect. They work very similar to that. But none of the other frameworks do it because basically all parallel frameworks in R, for historical reasons, been focusing on this map reduce, L-apply, and all these things. So the future broke that down and created the core of it, and then build it back up again. I also want to mention is the parallel backends. Of course, we can do sequential processing in all frameworks. Actually, turns out the parallel package doesn't have a sequential plugin, so you can't use par-L-apply sequentially. I never thought about that until the other day. We can do forked parallelization, which is this MCL apply. We can do that in futures too, called the multi-core. I ask you to be very careful about using that. You can read about this at the end of the tutorial in the appendix. But it works magically, but it's PSOC we saw, the call-R parallelization across multiple machines. You can do in all, but it's, I would say, with the future framework and the parallel package, it's very simple. The other ones, it's kind of tedious, unless you use the do future backend and HPC schedulers. That the bias parallel package can do that now also since 2 years. Okay. I'm going to skip random number generations. I want to say open to discussions. If anyone want to come online or ask a question in detail, this is, we now have 10 minutes to do that. So please do that. I will skip forward to, I think there was a question, what about MCL apply early on? And I can take, for instance, exception handling. Actually, let me start with the first one, the most important, which I mentioned. Careful with fork processing. So MCL apply use something called fork processing. This is an operating system thing. It works on Linux and Mac OS, but not Windows. And Windows, it will fall back to sequential thing. But more important, it's super neat. It looks like it works, and you don't have to. It just works. However, it might be very unstable, and it's also there's a belief that it's actually more memory efficient, but it might not be because of R's garbage collection and things. It might actually be more expensive. There are discussions on Biconductor about this too. However, if you want to do it, the way to do it in the future framework is to use multi-core. It used the same thing as MCL apply. But the problem is that it's known to be unstable in the RStudio console. So RStudio officially or semi-officially is advised against not using it. It also doesn't work well in other graphical user interfaces. It might conflict with multi-threaded codes. If there's other packages you load, they might actually break this, and it can be core dump or get very weird errors. So, and the author, Simon Urbanek, who's author of MCApply and RCore member, he said, like, be very, very careful when you use it. You have to be fully in control of everything you call. So basically, if you think about this, putting it in and package, which in turn depends on other things, you're not in full control, because those other packages might actually get updated and all of a sudden yours breaking. So it's unfortunate. But then it also has like this funny exception handling behavior. So let's see. If you look at an error, so here I'm creating this using strict square root, and this is the one that throws an error if you pass -1. And here in this case, I use, where did we go? I use x -1 to 2. So 4 values and 1 is negative. So it will give an error. But MCL apply doesn't give an error, it gives a warning. And people might not know about this. So basically, it just happily returns something. And what does it return? It returns the list we want to have, and 2 of the values are correct. But the other has this like try error object returned. So it's not a one-to-one replacement to lapply if you have errors or might get errors. So if you use this y elsewhere, you might get funny results or try to pass this further on to something else. So in order to detect these errors, we have to scan our values coming back, see is it try error, and then we have to create our own error for this. And so this is a very low-level thing. It's powerful, but it's low-level. So it's also very confusing. So that's one thing. So there was a question here. Can you use futures to speed up Markov chain Monte Carlo calculations? So I would generalize that. Can you parallelize Markov chain Monte Carlo calculations? And some of it you can, and some you can't. And then if you use futures per se, it's just futures can't do more than any other parallelization. So it's more rewriting your algorithm in a way that are the things you can calculate in parallel or look ahead, and then yes, you can use futures or any other parallelization framework. But that's a more like algorithmic question. See. Okay, this is a good question. Heather asked, do you always have to keep your main R session running to use future? Yes. I'm actually going to go in person here. Stop sharing so you can see me. Yes, it's we have to do that. So, and the most common one here is like when people use HPC schedulers, they use futures to launch, start R and run something, and it might take days or even weeks to finish on the scheduler, because they run huge genomic analysis. Right now, there's no way to log out from R and log back in and recover those settings, which is unfortunate. We're working towards it, so it's on the roadmap, and this is not just for this case. There are like other places too. It's we want to be able to launch workers, log off, close the computer, and come back a month later and pick them up again. So it will happen one day, but it will probably take a year or two. Yes, future can be used in a script submitted to a job scheduler, as long. That's a question. So future can't be used in a script to submit it to a job scheduler. It can. So the way you do, and I use it, it's like you launch your main job, your main R script, and that runs in parallel. And that in turn creates other jobs on your job scheduler. And that job will keep staying there until the other jobs finishes. And then your main job will complete. So that's how it works. Okay. Yep. This was super fun. Really great questions. As I said in the beginning, this was my first tutorial. I learned a lot, and I hope you also learned things here. Okay, any insights on missing globals? Okay, I'm worried that we have 2 minutes left here, so I'm worried that we're going to lose contact all of a sudden. I'm going to share my screen again. Oops. I managed to close my. Sorry. Okay, globals. Missing globals here. Very quick. Missing globals can happen. There is a whole vignette when it can happen. Most of the time it works, but if it doesn't work, it means that R can't figure it out by looking at the code. Examples is like if you try to have a function and it takes a variable and you pass the name of the variable as a string, there's no way R can figure out that the content of this string is a variable. So in this case, it will fail to pass this to. Do not zoom. It will fail to pass this to the worker, and the worker say, hey, I don't know what global A is. The way to do this is you guide the system. You say, add an A here and fake it. There are other ways to do it, but that's the gist. So there's a big vignette on that, but most of the time you don't have to worry about it. 45 seconds left. So yeah, thank you too. It's been great. Oh, Heather says you don't get kicked out. So well, let's see what happens. But if we get kicked out, I will say it might be that the recording ends, but I will stay on after the 20 seconds left if anyone want to stay on. Thanks for the kind words. And can go into more details if anyone have that. You're welcome, everyone. Do you plan to do more tutorials? Yes, especially after this one. No, it's, yeah, I will. Okay, seems like we're still here. Okay. Bye-bye. So if someone want to stay and talk for details, I will hang on. But I understand if you want to move on. It's been a long day. I have a few more things that can be said if you have questions around them. It's I could just show what I have, or if you, okay, let's see. For random number generation, can use other methods than the default one. Okay, let me bring that up. Okay, plus for random number generation. Okay, that's good. So let's see. I'm not sharing my screen yet. Got to share my screen here again. Okay. Okay, I have to do, sorry, I have to. Okay. So random number generations. What was the question here? Let's see. For random number generations, can you use methods other than the default ones? So I'm not sure what we mean by default here, but when we do not, we're talking about the type RNG kind here. So the default when we load R is we use the Mersenne twister. Okay. So that doesn't work. It works, but it's not designed for parallel processing. So means that if we try to use random numbers in parallel, there's a risk that we end up with poor random numbers when we look at the whole set that we do across parallel. We might have random numbers that are somewhat correlated in two different workers. So our statistical methods that rely on random numbers might get biased results. So it's important not to use that. Instead, R has the Lecuyer method that's specially designed for this. Are you aware of this? Who asked the question here? Okay, so that's the question. Can we use something else than Lecuyer? Right now, no. Again, on the roadmap, it hasn't been. Yeah, no worries. It takes time. We have plenty of time here. It's so the Lequier is the only one that the future framework supports now. I would say that's time. I'm aware that there are other methods out there for parallel random number generations, and ideally there would be a way for you as the developer to say, I'd like to use this method instead. It can definitely be done. I mean, we can update the future core to support this, but right now not. And I think it will take a while before that can be done. So if you need something else, you have to roll your own, which can be done, and that's how you have to do it when you do parallel apply and those things too. You can pre-generate your parallel streams or seeds to your parallel streams and pass them over to your futures. So you can still do it, but you have to do it manually. I hope that answered your questions. I would be curious which one you like to use instead. I only know so much about parallel random number generation, so I'm keen to hear people who know more. And I would love to see someone producing actually, it would be like a blog post or a paper showing like why it can be very bad to use the built-in one in the default Mersenne twister in parallel processing. Theoretically, I understand how it can happen, but I would like to see some results where it actually gives the wrong results. So that would be very interesting to see. But I can say that if you like to use this parallel one, it's very simple. Oh, cool. So when you say, I had a simulation recently where our default gave the wrong results, and here you mean the default Mersenne twister. Yes. Yeah, that's I'm using it in parallel. Yeah, I mean, please, if you, I would love to hear about that. So please reach out to me if you can show how it worked, or if you want to write a blog post on it, you should consider doing that, because that's super important. The thing is, like, most people don't want to think about this and just use whatever is the quickest, and then it might be like months later you actually discover it's because the wrong random number generation was used. So it's a very, very important question. So the way it works in futures is only thing you have to specify is like seed equal to true. That's basically saying I need to use random number generation. It could be RNG equal to true here, but it's not. We ended up using seed. So that's how you tell future framework to use Lequier, and it will use that. It respect the global seed you have in your thing, so you can get reproducible results like this. Well, the update here for the people following, I don't know if we're recording still, but if someone is seeing, it was a shocking difference in the results when using the default Mersenne twister in parallel. Great difference. So yeah, if you don't declare seed equal to true with futures, future will nag you. It will say, hey, you used random numbers here, but you did not declare it, so your results are probably unreliable. So this would have helped you if you used this at least, or caught your attention. I don't know if Lequier would have probably been better, but maybe not good enough. The reason why this is not the default is that it's actually quite expensive to generate these Lequier random things in parallel. So if you don't use random numbers, it comes with a significant overhead, but it's very cheap to test if they were used. So that's what the future framework used, and that was a great suggestion from one of the future users and developers added a few years ago. And okay, on the report from the user, so yeah, Lekia seems to have solved things, but I heard that there were other options, so just wanted to look into it more. Yes, yeah, there are other options, and there is more research developed. So, and they're packaged on CRAN that provides additional options in R. And these things you have to declare seeds also when you use future lapply or the RNG. If you don't, you get an error too, or warning explaining that. So that's one way how the future frameworks try to hold your hand while programming, so you don't have to worry about everything. Cool. Yeah, you're welcome. I'm happy to be of help. It's should we wrap up here? Any more questions? I will try to put this tutorial available online in a nice book down format, and you already have the link, so I will do that by the end of this week, the no latest. Keep looking at the webpage and you will see it. Okay, thank you all. Okay, no more questions, let's finish. Take care, bye-bye, and enjoy UseR.